All right, so last time we went through Delaunay triangulations and Voronoi diagrams. We went through some of the basic properties of these data structures, and we came up with a couple of different applications for them. For example, we could, using a Voronoi diagram, find the closest point in some collection of points by simply locating which cell in the Voronoi diagram contained that point. And so this basic problem of locating a point in some sort of planar map, right, whether it's a triangulation or some decomposition into polygons, is what we're going to talk about today. So the goal for today is point location. And this is a very important problem. It's been studied in a variety of different contexts. It's extremely hard to do outside of planar maps. So once you get beyond 2D, it's really, really tough. I actually don't know of any great way to do it in 3D, really. I would say that this is probably one of the reasons why 2D computational geometry turns out to be so much more effective than higher dimensional geometry, is that we can often do these point location problems very quickly in the plane, and we really can't do them so well in the high dimensional spaces. And so the data structure that I'm going to cover today, we'll go through a couple of them. We'll start out first by just looking at a couple of different approaches to the problem if we go in cold and we're not allowed to do any pre-processing. And then we're going to look at a few different data structures which use either some sort of incremental construction or maybe some large construction. And then probably tomorrow, I think we'll see some really interesting solutions to this problem. But the approaches today are reasonable, right? They're just, we'll see some other ways to do it later. But first, we need to actually define what we mean by finding a point in a region. So we have this kind of concept here of a planar map. Decomposition, which we'll think of as being something like a cell complex, except we're no longer going to require that each of the faces of this map are going to have to be convex. Right? So this could be something like we have a bunch of different balls or blobs, right? And they're all glued together. They could even have holes inside them. Something like this, right? So we have some crazy, we'll just say that it's a partition of the plane, R2, into disjoint regions. And then the boundary of each of these regions is going to be some polyline, right? So it's just going to be like a collection of line segments. So examples of these planar decompositions are pretty ubiquitous. So if you have, say, like a map of the entire world, you could imagine that each country maybe chops up the world into different regions because most countries claim sovereignty over discrete regions of the Earth, right? And the problem that we have is that we'd like to say, well, okay, maybe these are all different countries. So if I say throw a point here, very quickly tell me which of the countries my point happens to be contained in, right? So that's the idea. Now, in the case where we're not allowed to do any pre-processing, we'll just consider first the situation where we go in, and you're just given this data structure, and then you want to just scan through it. You haven't looked at it yet, and then tell which point you're inside in the map. The only way you would really be able to do that is, in a sense, by just going through region by region and then just testing if the point is inside any region along the way. So this leads us to a sort of simpler problem, which is this problem of testing whether or not a point is contained inside a polygon. So this is the simpler problem. And the first one that we're going to look at, it turns out this is not much harder than the point in region problem because we could think of just testing each polygon independently and then locating the point inside whatever polygon we're looking at, and then that would be sufficient to do that in the brute force case. And it turns out when we even start looking at data structures for solving this, it's basically the same complexity to test if a point is in a polygon as it is to test if it's in some region. So this is the idea. Or more generally, point in curve. And so here's kind of the topological picture of what's going on is we have some region here. Call this omega. And we have this curve, which is oriented here, which is the boundary of omega. And so the idea is, given the boundary of omega and x in R2 is x in omega. All right, that's kind of the higher level picture here. So it's sort of like we're just given this boundary of some region. It's oriented, say, counterclockwise, or in this case, I guess it's clockwise, right? And we just want to say, OK, I'm going to throw a point in here. Check if it's inside that space, right? Or maybe try another point here. Maybe it's not inside that space. OK. So that's the high-level description. Now we could continue with this and maybe imagine some harder situations. So for example, there could be like a hole in here, right? And then this hole would be oriented in some way. And we could have like different islands out here. To get started, though, we're not going to worry about those cases yet, though we will get to them eventually. And we're going to assume that omega is completely contractible, right? So that it's a disk. So for now, assume omega is contractible. And this implies that the boundary of omega is a circle in a topological sense, right? So it's basically a 1D sphere. So, OK, that's the concept right there. So one way that we can try to test if a point is contained inside one of these regions, or inside omega, given this boundary curve, is we can use this concept from topology called a winding number, or it's sometimes called the degree of a continuous map. So maybe you guys have heard of the concept of a degree of a polynomial. In the same way, the degree of a continuous map from a sphere to itself generalizes this idea, right? So we can take any map, right, from a sphere onto itself, and we can assign to it this number called the degree. Now, this idea is actually very general. It works for arbitrary dimensional spheres. But the sense in which we're going to use it today is just for a circle. And when we talk about the degree of a map from a circle to itself, this is called the winding number. So this is the first idea, winding number. So here is the concept. So we'll say, OK, right. So first point, let's suppose we have a curve like this, right? This is C, right? And we'll say C is a map from, say, the interval, or from the one sphere, the circle, into R2. So we'll say, given this, and a point P in R2, we're going to construct a new map C star, which is the projection of C onto an infinitesimal circle located at the point P. So here's kind of the idea, is that we'll take a point here, right? And then what we're going to do is take this map, and for each little segment here, we're going to project it onto an infinitesimal circle. And so as this curve walks around it loops back and comes over there and turns into some little squished curve that's sitting on like a tiny circle centered at P. Or if P was inside here, then as we look around, we'd see that we have some curve that follows there, goes back, comes along, goes back, and then winds into itself like that. So some sort of like weird potato-shaped thing smashed to the sphere. And assuming that P is not on the boundary of omega, which I should have specified up there, but we'll just assume it because it's necessary for this to work, then we could project it to the sphere by just dividing by the length of the vector from P to the point on the curve. So we'll call this new curve, C of t, to be just C of t minus P divided by the length of C of t minus P. So we have this map C star, right? And now C star, instead of being a map from a circle to the entire plane, it's now just a map from the circle to the circle, right? So the type of C star is circle to circle map. OK. So I'm going to erase this stuff down here. Should have probably written that first, but that's OK. All right. So given such a curve, what we can do is we can count the number of times that this projection of the curve onto this tiny circle wraps around itself. All right? So the idea is that we're going to just keep a little counter, and then as we walk around the circle, every time we make a complete loop, going clockwise, say, we'll increment the count by 1. And if we ever walk the other way, then we'll decrement it by 1. Right? And this is sort of an infinitesimal property, right? So we're looking at just the incremental change in the angle of the circle as we walk along it, right? Which, if we think of this thing as being parameterized from 0 to 2 pi, the change of it is just the derivative, right? And then we're going to integrate that over the entire circle. So the degree, or winding number, right here, so the degree of this map C star is equal to 1 over the length of this circle here, right, which is going to be a unit circle, parameters from 0 to 2 pi, followed by the integral from 0 to 2 pi of the derivative C star dt dt. That's the idea. So we can think of this as we're just marching along, as like say, a parameter t, right, where this is the angle. So we're going to assume that the two curves for now, right, are basically parameterized by them. If we stuck the sphere into R2 here, we'd have to take an arctangent or, use some trig function in order to project it back into an angle form. So in the angle form, we're just going to integrate around the circle, keeping track of the orientation of the curve. And then when we're all done, it will be some integer multiple of 2 pi times that we've wrapped around the circle. And so this thing is an integer which counts the number of times we wrap around a circle, right? So this counts the number of wraps, also called the winding number, which equals number of wraps. OK, so what does this have to do with testing if a point is inside a polygon or not? Well, it turns out that if we wrap around this curve an even number of times, then we're not going to be contained inside this curve. And if we're wrapped around some odd number of times, then we'll be inside the curve. All right? So why is that true? Well, let's look at this case of this point on the inside here. As we walk along the curve, going through this whole loop, we eventually make one complete loop, or one circle, around this entire curve. And so the degree of this curve when projected onto this point here is 1, right? If we take this point here, though, which is outside the curve, right, then we loop back and forth over here, but we never even get around to making a complete loop over the entire curve. And so the result is that the degree would be 0. So here, the degree at this point is degree 1. Here, our degree is 0. And so the conclusion, right, And we could also imagine cases where maybe we had a curve where it looped around multiple times, right? So we could have something where, say, the curve loops like that, some screwy way. If we take a point here, and then we march along with the curve, so we'll start here with this point. So we'll go down, around, through here, come back, through, let's see, we loop there. OK, so we go, no, right, so we go back that way. Shoot, did I get confused here? All right, so we start there, we go around, yeah, to there. Right, I think, let's see. So we make one full loop there, one full loop there, then a negative loop there. So we actually have a winding number of 1 at this point. I think that's...
Is that, like, realizable in actual space, though?
These are just curves, right? So of course you can draw a curve in any space, right? But here's the idea, is that if you think of these regions, right, we can just count the parity of each time that we loop around it. So here we can imagine if you fill it, this region could be filled, this region would be filled, and then this region around this point would be empty, right? It's kind of the idea. So if we had like some connected shape like this, we took its boundary curve, right? Then this would be like an actual, boundary of some region in the plane, right? So it's totally realizable in this sense. So this is kind of the idea, is that we can say, okay, of the degree even, we'll say that this implies outside, and then degree implies inside.
Well, when we're talking about like 2D like space.
Yeah, for 2D curves, right? So, yeah, this is.
It's just 1 or 0, right?
Well, you can have a loop, right? So, like here, if you look in, here's like an example. I'll show you one where it can be like looped multiple times, right? So we'll just draw something like this. You can just like loop in like a spiral some number of times and then come back to where you started. And then your winding number can be like, say, 3 or 4 or however many times.
Yeah, I guess I'm still not, well, I'm saying like if you have like, we're still talking about polygons, right?
Yeah. So here's like a polygon, which would do that. You start with like a triangle, then you make a bigger triangle like that. Right? And then you come back here, then you make another big triangle. Here you make a bigger triangle. So you can just build like some crazy nested like loop of triangles that are all stacked inside each other. Now, I should say that there's probably a definition that you might be grasping for here, which is the concept of a simple polygon. All right, so there are 2 big classes of polygons. I mean, well, outside of convex polygons that we've been looking at so far. After convex polygons, there is a more general concept of just a loop of edges, right, which is just the basic definition of a polygon. But in the space of polygons, they can be broken into polygons which are simple, which are basically contractible regions, and then polygons which have self-loops, right? And these would be complex polygons or general polygons, right? There's usually like no special distinction made there. And so this formula for testing if a point is inside a polygon or not works regardless of whatever type of polygon you give it as an input. Right? So this is a very generic and standard definition. To illustrate why this might be kind of useful, right, or to have some definition, is that sometimes you can have really crazy looking polygons where it might be really hard to test whether or not a point is inside it. So you could draw like some weird like mess of a maze, right? And then it becomes kind of crazy, okay, well, if I take a point, am I inside the polygon or not? Now you have to kind of look at a bunch of different things, and it becomes a little bit messy to see, just by like looking at it locally, whether you're inside or outside. Right. So, okay. So that's this concept of a winding number. Now, the way you would implement something like this is that you would just loop over each edge of the polygon, and then you could just keep track of this change in angle for each edge, and then sum those up as you're integrating along the side of the polygon, and that'll give you, the winding number for that polygon. But the problem with doing that is that it's, first of all, not numerically so well behaved, because we have to compute these arctangent functions and then do this inverse trig in order to keep track of the change in angle. There are ways you can fix that though. But the other problem with it is that if we start adding in things like multiple regions, right? So say we have something like this here, or maybe we punch a hole that's not connected to the polygon there, then we wouldn't be able to support point testing, with these more advanced types of features. So if instead of having just a single loop for our polygon, we actually have multiple loops, then this definition of a winding number won't work just out of the box, right? So we need some other more general type of algorithm. So one way to do this is to kind of reverse engineer what the winding number is actually doing here. So I'm going to draw another picture. Drawing a lot of weird kind of pictures today. That's okay. So here, sort of what the winding number really does, right? Guess I'm going to erase this section here. Yeah. And, right. So imagine I have a polygon that looks like this, right? And I want to keep track of the winding number from a point here. Well, let's suppose I start integrating, along this point right here on the polygon. Then initially, as I start going upwards here, right, when I cross this section of the terrain, right, then my winding number is going to go up by 1. Similarly, when I go down here, it's going to go down by 1, right? So each time I go up one of these curves, it increases. And then each time I go down a curve, it decreases, right? So I just have to look, in a sense, along this one axis, and then I can just count how many times it goes up or down each time I walk along the full circle, right? So this would basically be each time it goes over here, it crosses from being 0 to from being say negative to positive, or from positive to negative, this little sum that I'm integrating. So one geometric version of this is I can imagine that I'm just shooting a ray out along this axis, and then counting the number of times that I cross the curve, right? So alternate interpretation. This is the alternate point of view. Count crossings. And this actually turns out to be a more fundamental way to test if a point is in a polygon or not. Right, so you can actually generalize this to include things like holes and work in higher dimensional shapes, which don't happen to be deformations of spheres, right, which is the only case where this winding number technique will work. And so why is this true? Well, this is really a consequence of a mathematical result from algebraic topology again, called the Jordan curve theorem. So the basic idea of the Jordan curve theorem, so let me go erase these things. So this concept, Jordan curve theorem, we'll just say let omega, and this doesn't even have to be in R2, it can actually be in any dimension, be a region. Doesn't have to be connected, doesn't have to be contractible, can be whatever the hell you like, right? It's just any crazy subset of this thing, with the constraint, with the boundary of omega which is basically, we can think of this as like the curve or the polygon, which is determining the region, a manifold. What do I mean by manifold? Well, I mean that it doesn't have any cusps, right? So if we look at each point on the surface, it looks just like a disk, right, or basically Rd minus 1. So it looks like some lower dimensional real space. This constraint, you can get around it, but it makes things way more technical, and we're not going to worry about that. All right, so we're just going to leave it as manifold for now. OK, so with the boundary of omega a manifold, and let C be a curve with end points C0, C1. Then one of the following is true. True. So the first case here is that this curve crosses omega an even number of times, right? And it's going to cross it in a finite point set is the constraint. So we're going to say the intersection of C with the boundary of omega is even, and either both points on the end of the curve are in omega, or they aren't in omega, right? So they're both not in omega. That is, they're in the complement. So the idea is that if we take C0 and C1, then either they're both going to be here, right, or they're not in there, right? Or 2, the intersection of this thing is odd, and exactly 1 of C0, C1 is in omega. All right, so that's the idea, right? So we'll just think of this as that if we keep track of the number of crossings, then we can think of this as counting the parity of this inside-outside for each point in there. So imagine we draw some region like this. Let's say we take 2 points right here, right? Then I can draw any curve I like. I can draw like a ray that connects them. I can draw some curve that goes through it like that. And it doesn't matter which curve I pick, the parity is always going to be the same. So for example, with this one, I cross out, now I'm outside. I cross in, now I'm inside. Cross out, now I'm outside. And I'm finally outside, right? Similarly, I start inside, I cross once, now I'm outside, still outside, right? Or actually, I guess I kind of intersected the wrong curve down there, but you get the idea, right? So we're not going to prove this theorem, right? I mean, we're just going to kind of make an appeal to a higher power of algebraic topology, but it's true. And it works in higher dimensions and wherever you choose to apply it. And the consequence of this is that we can test whether or not a point happens to be contained inside a polygon by just shooting a ray and then counting the number of times that we cross each boundary segment. So that's the idea there. So how do we turn this into a concrete algorithm? Well, first of all, in 2D, yeah?
Do we have to specify somewhere that the region is closed, or is that?
No, it just has to be, well, the boundary has to be a manifold, right? That's the only real constraint that you have to have, right? So you have to have this property that you only have like the other thing. I mean, there are actually like some more technical constraints that you have to say here. Like one that I forgot to mention here, but we have to be a little bit careful about it, is that you can't have these sort of like glancing things where the curve touches the surface like that for some extended length of time. It has to properly cross it in exactly one point. We're just going to assume, though, that that doesn't happen for now. So we're going to require that when we intersect these two things, we get a finite set of points where it intersects exactly, right? So we can't have like a little thing where it touches like the thing and it's just tangent. It has to properly cross it. So that's the only kind of like real constraint. And then also these C0 and C1, they can't be on the boundary of omega, so they have to actually be, properly separated here. Right? But if we have those conditions, then this works. Right? That's the basic idea. All right. So there's a couple of like little asterisks here, but it becomes a little bit of a mouthful to say all of it. That's the idea, though. Right? So this hopefully is intuitive, right? This theorem. Okay. So, and if you don't believe this is a real theorem, it's actually been proven by computer, right? So this theorem has actually been like mechanically verified. Like people, translated all the axioms of topology into, axiomatic set theory, and then, typed it all up and ran an automatic theorem checker on it, and it's true, right? So, okay. So how do we turn this into a practical algorithm for testing if a point is in a polygon or not? Well, all we have to do is just march along each edge of the polygon and then check whether or not a ray shooting out, say, along the horizontal axis happens to intersect the polygon. So here is the idea. So point in polygon. Is going to be shoot ray along x-axis. All right. So I'll we can sort of use this picture as inspiration, right? But we can imagine that, say, these are all edges. And so we have to just kind of, check which of them happen to intersect. All right. So how do we do that? So we'll call this routine PNP for point and polygon. And we'll start with a polygon capital P, and we'll take a point Q for a query point. And so initially what we're going to do is we're going to set this flag inside to false. All right? And I'll say for I equals 0 to n, so we're going to loop over all of the points. Set this point A here to be the ith point. B is going to be the I plus 1th point with cyclic indexing. So we're going to just look to the next point in the polygon. And then we're going to compute the orientation here now of the edge, right? So we're going to use that left-right orientation test. So here's the idea. Suppose we have a point here. This is our point Q. And this is our segment here. We'll call it pi plus 1. Then Q, this ray here shooting from Q, will intersect this segment if and only if it's contained within the x region spanned by here. So that is that within this slab cut out by the lower, or within this slab cut out by the y components of pi and pi plus 1, Q is sitting there. And if we do a left-right test from the lower point to the top point, it's oriented to the left, right? So we have to check two cases. The first is that pi y component is less than pi plus 1s. I guess I call them A and B here, right? Right. So here's the idea. So we'll say first if the y component of A is greater than the y component of B, we'll say swap A, B. Right. Actually, I don't even need this S thing here. And we'll say there's sort of two cases to consider. So we'll say if orient A, or the first case here is we'll say if AY is less than QY, I guess it should be less than equal to BY, right? So the first thing is we're going to check if Q is contained in this slab. And we'll say if orient A, B, Q is less than 0, then we'll just flip the parity here. And then when we're all done, we just return inside. OK. So kind of scrolled off a little bit there. But the basic idea is pretty simple, right? We just loop through each segment, check if we happen to be contained in the slab here. If we're in the slab, then run the orientation test, right? So you can calculate this exactly. No rounding errors, no problems whatsoever, using any of the techniques that we've talked about so far for doing robust orientation tests. So, OK. So that's fine. This is actually pretty much as good as it gets for a polygon point membership test, because we have to check every vertex of the polygon, or at least every segment. And so this is an order n algorithm. And it doesn't get any faster than that. Now, there's another way that we could think about this. It wouldn't optimize this algorithm. It would probably make it slower. But if we look at this polygon as being an oriented loop, right, then in some sense, we wouldn't actually have to cast a ray against every single segment over here. We could just shoot a ray, and then when we hit this first segment here, we could just test if it was going up, basically oriented left or oriented right. And then based on that information, we would be able to immediately determine whether or not it was inside this polygon or not, right? So is everyone kind of on the same page with that, right? Or is this?
Can you say it again?
All right. So this is important. So I'm going to erase this segment here. Is this all clear so far? All right, this point in polygon test.
Real quick, sorry, this is really stupid, but if the orientation ABQ is less than 0 as a left turn?
That's what we're going to assume here.
Okay.
Yeah. So we're just checking if Q is to the left of orient AB, right? Because basically, if it was over here, right, the other situation is that we always know A is the other point. So we'll consider the alternate configuration. So here is A.
I was just trying to remember which is left and which is right, if it's positive or negative.
I don't know if I've even been consistent in this course. For now, we're going to define it to be left, right? This is all we need, is we just want to check that Q is to the left of AB, all right, with A at the bottom.
Fair enough.
All right. It doesn't matter, OK?
Yeah,
I
guess it only has to be, you could still put greater than 0, and then you just be
exactly. You just switch the greater than to the less than, or put a negative sign in front of it, Or you could actually even change the swap test, right? But then you have to change that. So I don't know, whatever. There are many ways you can just flip the orientation and it'll work. One of them is just, if you get...
For this particular case, yeah, you can really just do less than equals 0 or greater than equals 0.
In fact, in any case where you're confused about the orientation, you can always just put a minus sign there, and then it's going to be the other orientation, right? So that'll, fix it right there. So, OK. So that's how we do it for polygons. I think we're done with that part. But I want to point out that there is another way we can think about this, where if instead of shooting a ray that goes through all of these points, we can imagine that we just shoot like a tiny ray here, right? That only goes to, say, this point here. And then if this edge was going up, we would be inside this polygon. And if it was going down, we're going to be outside the polygon. Or I actually would like to draw it going another way. I'd like to draw the ray going to the top rather than to the side, because it's going to make a series of figures that I'll draw later much easier to understand. So imagine here is our polygon. We're going to have oriented edges here. OK, this is a convex polygon. Admittedly, there are easier ways to test if a point is inside it or not. But I will take this point here, and imagine I shoot the ray straight up, and I just record the first edge that I hit. If the edge is going to the right, that is, that if I go from, like, say, if I run an orientation test and it tells me that I'm to the right of the edge, then I'll be inside there. Or similarly, if I shoot another ray and I go straight up and then hit a ray, then I can just test if I'm below that edge, right? So here is kind of the trick, right? Or the thing that we're going to apply here. The trick. If we just cast a ray and stop at the closest edge, then PMC is equal to the orientation. So that's the idea, right? So all we need to be able to do, in a sense, is if you can say, given some collection of line segments, right, pre-process it, so that given a query point, you can find whatever segment is directly above it. That's the trick, right? So we're going to try to figure out how to answer this problem. So this is the idea, right? So PMC is equivalent to being able to answer this vertical ray query, right? Or actually, or the way I want to write this is actually I want to say that vertical ray queries point membership classification, right? That's the idea. So this is what we want to do. We want to build data structures for answering these vertical ray queries, because if we can do this vertical ray query fast, then we can do point location really, really fast. That's the idea. All right. So how are we going to do this? Well, OK, first of all, dumb ideas. The first dumb idea, right, is that we could use the Dobkin-Kirkpatrick hierarchy to do point location, and then that would actually let us solve this thing, right? But the problem with the Dobkin-Kirkpatrick hierarchy is that, first of all, it only works for triangulation. So if we wanted to do it for some collection of line segments, we would have to triangulate them first, and that actually turns out to be pretty complicated and kind of annoying to do. The second problem with that, though, is that the constants involved in the Dobkin-Kirkpatrick hierarchy are pretty enormous, which make it not so practical compared to other techniques for just doing these vertical ray queries. And finally, and this is going to be a problem which will be common to the techniques that we'll see today, but not the ones that we will see tomorrow. The Dobkin-Kirkpatrick hierarchy is only a logarithmic time algorithm in expectation, which means that in the worst case, and actually even in reasonable situations, you can run into situations where it might take much longer than, like, say, log time, right, to get a query. So we would like to find algorithms which run in, say, like worst case log time. And we can do that, right? Here, just as a simple proof of concept that this is possible, there is a very trivial data structure that we can apply to some collection of line segments which allow us to answer these ray queries in log time, right? It turns out to be not practical for other reasons, but we'll see them in a moment. So here is the simplest, fast data structure for vertical ray queries. And I think my pen is starting to die here, so I'm going to go switch to blue from now on. So simple data structure for vertical ray queries. All right, so here's the concept. We're going to start with some collection of line segments here. They don't even have to form a polygon, right? Because we're just going to do this vertical ray query. Whatever, right? OK, so here's the idea. So first, sort all endpoints by, say, x, right? So along the horizontal axis, we're just going to sort them left to right, all right? Yeah, we'll just sort every single vertex in the entire set of segments left to right. And the second thing is cut segments at each endpoint, or cut segments between successive endpoints into slabs. So what do I mean by this? Well, here's the idea. What we're going to do is we're just going to draw a vertical line going through each endpoint. No. we could use that. That's another data structure. But there's actually even better ways to do it than that. We'll see them. No. There's better ways. We won't see them today. We'll see them next time. All right, so here's how you do this, right? So now we've cut this thing into all of these different slabs. Suppose we want to locate a point, right? So suppose I take a point right here, right? Well, I can figure out which of these slabs that I'm in by a binary search, right? So in log n time, I can just binary search, find a least upper bound or a greatest lower bound or whatever, right? And find this slab that contains them, right? So this will be, say, like slab xi. Now, what I'm going to do then is within each slab, I'm going to take all of these segments, right? And the one thing I know is that within a slab, there are no endpoints, right? Because all of the endpoints are at these boundaries of the slab. And so that means that no line segments here happen to cross, right? So I can sort the line segments along y and store that in a binary tree, or just a flat array, right? So for each slab, sort segments in slab by y, right? That's the idea. So this slab here, right, that if I expand it out here, will look basically like a binary search tree, or if I flattened it out, it'll be an array, where, say, the middle one, we'll call this guy, say, slab 0, slab 1, slab 2. It'll look like, say, S0, S1, S2, right? Yes, it will, right? We'll get to this in a moment, right? But that's the problem with this data structure. So if we want to locate this point here, right, we can first find the slab that we're in log time. And then within each slab, we can just do a binary search on this array. And then we can figure out which slab is directly above it, again, by another binary search, right? So this would take log time. So we have log of the number of endpoints here, which is just log n, and then log of the number of segments for these things, which is definitely at most log n, right? And so the total complexity is just log n. So the conclusion of this is basically to search, first do search in slab, which is an order log n operation, and then 2, search in slab, also order log n. Worst case in both cases, right? So no expectation, no like weird, like kind of amortized argument or anything. Hard log n. Problem with this, though, is that the time complexity for doing all of this is going to be quadratic. Or the space complexity for this whole data structure is quadratic. So the problem is that the size will end up being order n squared. Why is that the case? Well, you can just draw kind of an example to see where this goes horribly wrong. So imagine that we have a bunch of segments like this, say order n of these, then draw another order n segments that look like this at the bottom, right? Just walking in this thing. Then each of these slabs here, when we cut through it, is going to have n segments up there. There's another n segments down there, quadratic space, right? So this data structure is nice in that we can use it to get very fast queries, but it's probably not a great idea because it's just going to be enormous, right? Yeah?
Can your segments cross each other?
No, we're assuming that they don't cross, right? Because, well, remember what we really want to do is we want to do point location and planar maps. And these planar maps, they're basically decompositions of the plane. So they're never going to have any crossing segments, right? They're all just like, disjoint regions, right? So at most, you'll have a segment which is a boundary of, say, like 2 different countries or 2 different Voronoi sites, right? And then you would basically just do this like ray query and then figure out which Voronoi site or country you happen to be contained in. That's the idea, right? So, OK. So this data structure doesn't quite work. So
also, the complexity of actually pre-processing, wouldn't that be like n squared, maybe even n squared log n?
Nah, it should be n squared log n, right? Because you have to build each slab, right? And the size of each slab is going to be order n, and then building the slab is just a sorting operation, so it would be n log n. this is more of a theoretical idea, but we will return to this. It turns out that this idea is actually not far from being a really nice way to do this searching, right? But we will get to that on Tuesdays when we'll get to see how this works, right? But that's not the technique that we're going to talk about today. Instead, we're going to talk about a different kind of idea, which will give us log n expected query time. And it uses this technique called a trapezoidal decomposition of the plane. And so this is an idea which turns out to be very useful in a variety of different algorithms, right? It shows up all over the place. And there's a bunch of neat things that you can do with it, including point location as one of the many operations. So it's worth understanding it.
I just have a quick question. Couldn't you just only store the lowest one in terms of y, and then you could just have it add memory, and that kind of solves everything?
Well, because remember, we can query like into the middle of the slab here, right? Like that's the problem. So if we were just looking at the lower envelope, that wouldn't, I mean, we could actually just store like only the bottom points, right? We wouldn't even have to store half of these damn slabs, right? So it's, it's not even really a big deal. Now there's, maybe if you think about that idea a little bit more, you can actually turn that into a reasonable algorithm. There's this technique called a monotone decomposition, which we probably won't cover in this class, but the idea is that you sort of split these things into like chains, right? That are all monotone in one axis, and then you can just do successive searches on these monotone chains in order to locate the point. We're not going to go into that, though, today. We're not going to worry about that one. There are other ways to do this, though. There are many different data structures, because this is a very important problem. Right. OK, vertical ray queries, trapezoids. OK, what do I mean by a trapezoid decomposition? How does this work? And how are we going to use it to solve our problem? So there's actually two parts to the trapezoid decomposition, but I'll first say why trapezoids and where they come from. So let me get a picture out here. All right, so the idea is that given some collection of line segments, we can think of these things as doing something like the slab decomposition, except instead of extending these slabs indefinitely, we'll just stop the slabs when we hit one of the adjacent endpoints. So here, let me draw kind of a picture. Maybe similar type of thing as before. Something like this, right? And so the key trick to making the trapezoid decomposition work is that when we draw these lines here, or I think I did it in red, we stop when we hit one of the segments, which is above or below us. So we'll draw this segment here. Right there, there, and there. OK. And why is it called a trapezoid decomposition? Well, if you look at each of these little tiles, or like cells that are left when you apply the subdivision, they have parallel x sides, right? And so they're all trapezoids, right? This is the idea. So I should probably write up here at the top, trapezoidal map. OK. So what do we do with these trapezoids? Well, one of the neat things with each of these trapezoids is that if we look at any of them, right, we can think of them as basically having like two lists of neighbors, right? So we have all of like the neighbors which are going to be to the left of the trapezoid, and then all the neighbors which are to the right of the trapezoid. And so what we're going to do is for each trapezoid, we're going to store a pair of lists, right? We're going to have a list of all of your left neighbors and a list of all of your right neighbors. And then we can sort them by y on each axis, all right? So that's the idea. So for each trapezoid, we'll call this thing Ti. Right? So for each trapezoid, we're going to store the left coordinate. All right, so this is going to basically be like the x-coordinate of the left edge, right? we'll store the right x, which is the x chord of the right edge. And then we're also going to store a list, or basically an array, right? It'll basically be the left, whatever, binary tree, whatever you choose, sorted by y. And similarly for the right neighbors, so we'll have right n. Y. All right. So what you can think of this as doing, right, is that this is kind of building like a little network on this like graph here. So we have sort of connections going back and forth along each of these horizontal segments. And in a sense, we can use this to kind of quickly march along the horizontal direction of these trapezoids. So if we start marching in the x-axis, we'll be able to kind of connect along that way very quickly. But it doesn't tell us how we do the point location problem, right? So this is only half of the picture of the trapezoid decomposition. The other half of it, and in some sense perhaps even the more important side, is that there is an associated search data structure, which we're going to build on top of these trapezoids, right? So in addition to these trapezoids, we're also going to have this search structure. And this search structure is, in a sense, like the real reason that we actually build this trapezoid map. So on the other hand, we're also going to have this search structure. And this search structure is basically a binary tree which is going to store either points, lines, or trapezoids in the nodes of the tree. So the internal nodes are going to be endpoints, right? So they'll be vertices, right? Or line segments. And then the terminal nodes are going to be trapezoids. And the consequence of that is because the terminal nodes are all trapezoids, the whole tree itself can't get too big, right? So actually, here's maybe a simple question here, right? How many trapezoids are there going to be in a trapezoid decomposition? Right, so before I actually even get ahead of myself and say how this tree works, let's say, how many trapezoids? Any ideas?
Rough order n.
Yeah, at most order n, right? Why is that?
Each endpoint makes a couple trapezoids, basically.
Right, exactly. Like, look at a vertex, right? Worst case, this vertex can make 3 trapezoids, right? That's it. Like, each vertex can only touch 3 trapezoids in the worst case. So if we think of this as a function of like the number of vertices here, there's never going to be too many trapezoids. There's only going to be like at most linear, trapezoids in the number of vertices. All right. So the neat thing about this trapezoid decomposition is that unlike the slab decomposition, we're not going to have like an enormous number of nodes in our slab tree. We're going to just have like this tiny collection of trapezoids, right? And then if we can pre-process these trapezoids in some way that we can then search through them, then we will have obtained our fast query data structure for doing these vertical array queries. I should say the other interesting point here, too, is that if you've managed to locate a point in a trapezoid, you're pretty much done with your vertical array query. Because for each trapezoid, all vertical rays hit the same segment. All right, so all you have to do is for each segment, we can actually store the, should I actually go say here, we'll just say segment of TI, which is the answer to all, to basically a V-ray query in TI. So in a sense, if we have a trapezoid decomposition, all we have to do is locate the trapezoid containing the point, and then we already know the answer to the vertical array query. Right? We basically just look up the segment that's at the top of that trapezoid, and we're done. Right? So piece of cake. Right? How do we find the trapezoid? Well, search structure time. Right? OK. And the search structure is basically a binary search tree with 3 types of nodes. All right. So the first types of nodes are point nodes. So we're going to call these point nodes. All right. Now, the idea is that each point node we're going to think of as cutting the space into the space which is to the left of the point node and the space which is to the right of the point node. So we're going to have basically 3 values. We'll have 3 pieces of data here. We'll have the end point. We'll call this basically P. We'll have left. We'll have like the left subtree, which is basically all nodes left of P, right? So it's basically, we're going to think of this as it partitions space along this axis here, and everything to the right is going to be in the right tree, everything to the left is going to be in the left tree, right? So you have a right tree, which is all nodes. The right. Okay? And we're going to have line nodes. It's a similar kind of idea, except instead of partitioning space above or into the left or to the right, we're going to take one of these line segments, and we're going to partition the space above or below the line segment. So the idea is we'll have basically a line, L, right? Which is basically one of these like line segments. We don't even have to store the endpoints. It's just a line, okay? And then we're going to have above, or I guess we'll just call it left, right, confusingly, maybe because we want to have left tree, right? We'll say that left is all the nodes above the node, right? So we'll say it's basically the above.
When you say all nodes above, are you?
Yeah, so I'll draw a picture here, and this will become probably more clear in a moment, right? The idea is that we're going to think of this like line here as splitting the space in some way. So if we think of the space, after restricting to the endpoints, right? Then within this space that's carved out by all of the nodes above this tree, right? So it's sort of partitioned off. Then we're going to cut the rest of the space here into 2 regions, the stuff which is above the line and the stuff which is below the line. And so we'll have this right segment here, which is the stuff below the line. And then the leaves are basically trapezoids. So right, and then this is just going to be the stuff here, right? So this is what we're going to store in our tree, right? It looks a little complicated, but once you start kind of playing with the details here, I think it becomes a little clearer. So I'm going to draw. I want to erase this and draw a slightly simpler picture here, because if we try to draw the trapezoid decomposition, it's going to be a little messy. So I'm going to erase this stuff with the trapezoids. Does everyone kind of have the idea here with the... Does everyone at least know the properties of the trapezoid? We have the left x, right x, the left nodes, right nodes, and then the segment above it, right? That's
just real quick. When we say left neighbors, since is that bounded by how it's bounded by
The verticals. Or like topology types.
Well, I was just thinking.
you can think of, so usually it's not going to, typically, in the worst case, it could be pretty big, right? Here's why. Imagine you have like a bunch of x segments which are all have the same x value. You have another bunch over here. And so then you have like some trapezoid. Where did I put the red? Here we go. All right, so you can imagine that you have something like this, right? So here in this trapezoid, you could have a whole bunch of segments that are all parallel here, right? Or all have the same x coordinate, and then a whole bunch over here that all have the same x coordinates. That's why you have to store like a list, right? The simpler case, though, the easy case, is that if all of your points are in general position, it will be at most 2, right? Because if they're in general position, then no of these guys will have the same x coordinates, so you'll only ever have like just one segment that you're touching, right?
Yeah,
in general position.
I was just wondering because I figured you probably wanted to bound the overall memory usage.
Well, it doesn't. That turns out to be okay because this is basically a planar graph, right? And so we have n faces and then n vertices, right? And so we're also going to have at most n edges. And then each of these things is just an edge in the planar graph, right? So we'll basically run into the Euler characteristic formula, right? So we have v minus e plus f equals, some constant 1, right? So it's fine. So it wouldn't even matter if we have multiple things coming in and out of each of them. It's still going to be OK. Right. So OK, simpler example time. I'm going to draw a very tiny trapezoid decomposition. So this is the search data structure here that we're focusing on now. All right. And time. OK. Running a little low. It's fine. OK. Damn it. OK. Just 1 point. A pair of line segments. Fantastic. All right, we'll call it this point P, Q, R, S. Call this line L, and this line M. OK? So here's how we're going to build our trapezoid tree. All right, so let's draw the trapezoids here. Right. And we'll label them. Call this one A, B, C, D, E, F, and G. OK. So what does the search tree look like for this trapezoid decomposition? Well, it turns out there are multiple possible search trees that we can build, right? Just in the same way that there are multiple possible binary search trees that you can build on top of a sequence of n items. Okay? But the one that I'm going to draw for you here, I found in your textbook, so you can actually look it up there. But here's the idea. So we're going to start initially with a root node here at this P, right? And then we're going to cut this space into 2 chunks. So to the left of P, we have A, right? So we have like a leaf node for this trapezoid, right? A over there. And then to the right of this whole, like this line segment P, we got the rest of the stuff that's in the plane, right? And so what's to the right of it? Well, we can insert another point node here, Q, right? And then we're going to have the stuff to the left of Q and the stuff to the right of Q. To the left of Q, right, so these are all the points which are to the left of Q, all the points to the right of Q. We'll create a line node, right? So this is, we're going to draw point nodes with a circle, line nodes with a square. We won't draw anything around the trapezoid leaves. We have a line node here. So above L, we'll have a leaf node for B. And then below L, so these are all the points below there. Let's go put in a point node for R, right? To the left of R, we'll have a leaf node for C. And to the right of R, we'll have another line node here with M in it. And above M, we'll have D. And below M, we will have F. So that's F down there. Hopefully you can see that. So what's to the right of Q? Let's insert the point P here. So we'll start with a point node there. So we'll have S. Then to the left of S, we'll create another line node here for M. To the left of M, I guess we'll put an E node there. And then to the right, we'll have to connect this back down to the trapezoid F. And similarly, to the right of S, we'll have a node G. All right. So it's all well and good, right? I mean, we're going to basically have like extra like copies, right, when we go down to the trapezoids because we don't want to like double up on it. So that's the idea. So, okay, how big is this thing at the end of the day? Well, it turns out that if we enforce a sort of uniqueness property, right, then we can actually show that the number of leaves in this whole structure, the number of trapezoids, is just the number of trapezoids over here. And then we might have some duplication, right, due to these like extra pointers or edges sitting inside there. But it turns out that the number of duplicates that we're going to have inside this tree won't be too bad. And so by a very hand-wavy argument, because there's not a lot of time left in class, I'm going to tell you that the size of this tree ends up being basically linear in expectation, right? I mean, the sort of intuitive, hazy idea, right, if you don't look at it too hard, is that you have n trapezoids here, right? If you have a tree with n leaves, then the size of that tree is about order n, right? Now, this is not quite a tree because we have these like little loops and things going on in there, and sometimes the trapezoids show up multiple times, but it turns out they don't show up too many multiple times, right? That's the key trick in order to make this all work. All right, so it ends up being order n. Just going to have to take my word for this for now. We're not going to get to the proof of that today. Okay, so how do we use this crazy mess of a tree to do a query? Well, let's go through an example. So suppose I take this point here. Let's call it x. All right. So the way you locate a point in a trapezoid using this data structure is you just walk down this tree. So we start at this point P here, right? X is to the right of P. All right? So that means we now go to the next node in the tree, which is Q. So we have the node Q here. X is to the right of Q, so now we go down to this structure here. X is to the left of S, so we now go down to M here. All right, X is below M, so X is in the trapezoid F. Done. Okay? Everyone follow that step? Let's do one more point. So therefore, if we ran a vertical ray query from X, it will hit this line segment M, right? Because that's the segment for that. Let's take another point here, whatever. Again, if we run this point, it's to the right of P. It's to the left of Q. So now we're in this point. It's below L. It's to the right of S. It's above M, so it's in trapezoid D. Right? That's how we do the steps. So you basically say you get to a point node, you check left or right, walk down the appropriate subtree, you get to a line node, you check above, below, again, walk down the right tree. Okay. So far, so good? Question? Yeah.
Is that tree unique? Or
no, absolutely not unique, right? In fact, there could be all kinds of crazy different trees that you could build for like the same trapezoid decomposition. And now we're going to go through how you can build these trees. And there's only 2 minutes left, so we may not be able to do it in much detail. But I'm just going to sketch out how this works, right? Here's the idea. Suppose you want to insert a line segment into this tree, right, if you already had one. Well, what you can do, right, so I'm going to draw a picture here. Suppose I want to insert this line segment. Here's the general formula for inserting a line segment into the tree. Is you first find the left endpoint of the line in the tree. You just use that search algorithm I just described to you, right, by basically walking down the trees, which is essentially the definition of the search tree, right? Once you've located the left endpoint, then you use that trapezoid data structure that we talked about earlier to march along this line segment. And so when you're in this trapezoid, you can basically do a binary search to figure out where the segment crosses on the right side of the trapezoid. March over there. You locate now that it's crossing this trapezoid, and you just repeat, walking forward. And then when you're all done, right, you're going to have located all of the trapezoids containing this line segment. Then what you do is you prune those trapezoids out of the tree, and then you replace them with new nodes that happen to model these new trapezoids that were created by the line segment. Now, I'm hideously over time. Does anyone have places that they need to go after this? Otherwise, we're going to go into maybe like 10-minute overtime if you want to do that. Or else we'll just call it a day if you're happy with a crappy explanation. Because I didn't get to how you actually construct the trapezoid tree here. So yes, no. Poll, show of hands.
I don't have to go anywhere, but I'm just wondering if there's a class somewhere after us.
If they kick us out, then we'll just leave, right? That's the simple answer, right? Everyone's okay with this? All right, we're going to go on ahead. So we're going into overtime here because I went a little slow today. So here's I'm going to draw one more example here. Then we'll see how we do this. Right. Where did I put the eraser? OK. So we're going to draw a brand new example. Maybe when is your other class starting?
20.
OK. Maybe we may have to call this quits then. OK. You can find this material covered reasonably well in DeBerg. I believe there's a chapter there on point location, which covers this. We'll see another data structure for doing point location another time. Let me just finish up then by just saying a couple of quick things about what you can do with trapezoid decompositions besides point location. Here's one neat trick. If you have a trapezoid and you want to triangulate it, done, right? So if you have like a planar decomposition or some map and you want to triangulate it reasonably, you can just compute a trapezoid decomposition and then draw these diagonals, and now you've triangulated the thing, right? So it's pretty easy. Another nice thing is that because these trapezoids are all going to have these parallel x segments, if you want to do rendering of trapezoids, that turns out to be pretty easy to do. So like a rasterization of trapezoids in software used to be one of the main applications of trapezoid decomposition. So it's like for fast polygon rendering. Finally, if you have two trapezoid decompositions of two different polygons, you can use that to detect all crossings between the edges of the polygons relatively fast. This turns into a process of merging the two trapezoid decompositions together. So it's, in a sense, it's like you're inserting one tree into the other tree, then walking through them recursively. We'll probably see some variations of how to do that later on when we talk about BSP trees. But I think for now, this is enough to say about trapezoids. You should read the chapter in DeBerg to cover more details for the things that I did not get to in this lecture, unfortunately. Sorry about that.